understanding chemical bonding is foundational in chemistry, allowing us to grasp how atoms connect through electron sharing or transfer, forming molecules and compounds with unique properties. Lewis structures visualize valence electrons, aiding in predicting molecular structures. For carbon and oxygen combine their valence electrons for stable molecule formation. In the co-Lewis structure, a triple bond forms between carbon and oxygen, ensuring both achieve an octet, demonstrating the octet rule's role in molecular stability. For No2, nitrogen and oxygen atoms form bonds that require using a double bond to satisfy the octet rule, showcasing the flexibility in electron sharing. Formal charge calculations help identify the most stable Lewis structure by comparing valence electrons in atoms with their hypothetical free state electron configuration. In ozone, O3, calculating formal charges helps determine the molecule's most stable structure, highlighting differences between central and N-oxygen atoms to ensure charge balance. Formal charges, while not representing real charge separation, aid in understanding electron distribution, ensuring the selection of the lowest energy structure for molecules. The octet rule guides molecular formation by promoting electron sharing to achieve 8 valence electron configurations, crucial for second-period elements in organic compounds. Exceptions to the octet rule, such as incomplete octets, occur when central atoms have fewer than 8 electrons, particularly in elements with less than 4 valence electrons. Elements like Li, B, and B exhibit incomplete octets, forming stable compounds with less than 8 electrons around central atoms, challenging the traditional octet rule. Odd electron molecules like No and number to defy the octet rule, resulting in unpaired electrons in their structures, demonstrating the rule's limitations in certain scenarios. Expanded octet exceptions occur when elements, especially in the third period, utilize available d orbitals to accommodate more than 8 electrons, as seen in PF5 and SF6. Sulfur illustrates both octet rule compliance in SCl2 and expanded octet exception in SF6, showcasing its versatile bonding capabilities within different molecular contexts. The octet rule's limitations include unexpected noble gas reactivity, lack of molecular shape predictions, and failure to address molecule stability, necessitating alternative bonding models. Ionic bonds form through electron transfer, creating positive and negative ions. This process involves ionization enthalpy for cations and electron gain enthalpy for anions. Ionization enthalpy, electron gain enthalpy, and crystal lattice energy influence ionic bond formation, determining the stability and structure of ionic compounds. Ionic compounds typically consist of metal-derived cations and non-metallic anions, with exceptions like NH4+, forming organized crystalline structures through Coulombic interactions. The NaCl crystal structure exemplifies the orderly arrangement of sodium and chloride ions in a repeating pattern, highlighting the geometric precision in ionic compounds. The energetics of ionic bond formation involve balancing ionization and electron gain enthalpies with significant energy release during lattice formation, resulting in stable ionic compounds. The positive sum of ionization and electron gain enthalpy in ionic solids is balanced by lattice energy release, ensuring overall stability, as seen in NaCl formation. Crystal structures depend on ion size, packing arrangements, and charge balance, influencing the geometric organization and stability of ionic compounds. Different crystal structures, like rock salt, NaCl, cesium chloride, CaCl, and zinc blende, ZnS, illustrate varied ion arrangements, impacting ionic compound properties. Ionic compounds exhibit high melting points, electrical conductivity when molten, solubility in polar solvents, and brittleness due to strong electrostatic forces in their crystal lattice. Ionic compounds are vital across industries, enhancing food preservation, powering batteries, enriching agriculture with nutrients, and improving drug absorption in pharmaceuticals. Understanding chemical bonding is essential for predicting molecular properties, driving advancements in fields like materials science and drug design, and fostering ongoing research in chemistry.